Alright, this is the second part of Chapter 10 Practice Problems. We'll go ahead and jump right in with example 10.6. And it reads a famous Amos bite-sized chocolate chip. Chocolate chip. Should have ate lunch before this, huh? Anyway, famous Amos bite-sized chocolate chip cookie, weighing 7.25 grams, is burned in a bomb calorimeter to determine its energy content. The heat capacity of the calorimeter is 39.97 kilojoules per degree Celsius. During the combustion, the temperature of the water in the calorimeter increases by 3.9 degrees Celsius. Calculate the energy content, and that needs to be in kilojoules per gram of the cookie. Very similar to the last problem that we worked. Strategy here is to use the heat equation again. Q of our heat of our reaction is going to be equal to the negative of the heat capacity of our calorimeter times delta T. We'll use that general equation to calculate the heat released by the combustion of burn-in that cookie. Divide the heat released by the mass of the cookie to determine its energy content per gram. This would be pretty fun to do on some type of, like this famous Amos cookie, or, any type of food that has a label with energy content in it. And we can compare our results to the energy content listed on the side. We'd have to convert it to calories, because most of these are in calories, but you get the idea. Alright, so to plug this in, and this time with this, because we're given the heat capacity of the calorimeter, we don't need to do an experiment with water to figure out what that heat capacity is. So we can jump right to just this heat equation, plug in our calorimetry information, which is 39.97, and then it gives us the temperature change. It says it increases, so because it increases, we know this value will be positive, because the final minus initial would be a higher minus a lower. We do the math here, and we're going to get negative 1.559 times 10 to the 2 kilojoules. The question asked us for kilojoules per gram, so we can leave that in kilojoules, and then it does give us the mass of the cookie, which is 7.25 grams, so we can divide by that, and then we get our kilojoule per gram ratio. So this one, really just plug and chug, put your values in there. Energy content is a positive quantity. Really the sign is just if things are released or gained, but just having this as a positive value is going to be most reasonable. So one thing to think about, according to the label on the cookie package, so it does pretend, and let's say we did do this in a lab and we got some information, so it does give us this information. A serving size is 4 cookies, which is about 29 grams. So we can figure out what that would match to, and it says each serving contains 150 calories. Convert the energy per gram to calories per serving to verify our result. So we have this value here of 4.184 kilojoules is equivalent to 1 calorie. That's just an equality, like 12 inches in a foot. So this will allow us to cancel out our kilojoules and then give us calories. And then 29 grams, we would multiply that. And then we get 1.5 times 10 to the 2 calories per serving. And then it says it contains 150, which does match up. So usually the labels are slightly off, and they're not perfect and don't match up. Alright, let's take a look at example 10.7. It reads, given the following thermochemical equations, and it gives these three here with their respective enthalpy values. And this is nitrogen monoxide, ozone, nitrogen dioxide, what's called molecular oxygen, the second most abundant gas in the air we breathe. This comes from some types of pollution. One example would be our car exhaust. Also exhaust from different industrial plants would put this out. and it'll give nitrogen dioxide that can react with the oxygen in our air. It produces ozone. Ozone in the right environment can chemically break down back into molecular oxygen. And then some of that molecular oxygen can continue to break down into what's called singlet oxygen through some other pathways which aren't shown here. The singlet oxygen is extremely reactive with other things that could be in our environment, other types of pollutants, and it could cause some harmful reactions. But you can look up more info on that if you're interested. So there's lots of fun facts there you could find. What we're ultimately going to do is determine the enthalpy change for the reaction nitrogen monoxide plus singlet oxygen gives NO2. And how we'll do that is we're going to take these three equations and their enthalpy values, and we want to set these up so that they cancel out, and then we can ultimately get this from these. Now, how we can cancel it out is we can write these in reverse. If we write it in reverse, we're going to swap the sign. We can multiply or divide the coefficients, which we would also need to multiply or divide the enthalpy value. So we're going to play with these a little bit and ultimately get to this equation, which is the strategy. So let me read the strategy and read along with me. Arrange the given thermochemical equations so that they sum to the desired equation. Make the corresponding changes to the enthalpy changes and add them to the desired enthalpy change. It's kind of weird at first, but once you actually look through a few of these, I would predict that they'd be fairly easy for you. All right, so let's just jump right in. We'll take the first equation. We have nitrogen monoxide as a reactant, which matches the desired equation, which is this. So write this down if you haven't already, and this is what we're going to lead to. And then you can get an idea of some things you can do so that we can generate that. So we wrote this out just as it was written on the first slide, or the slide before, and then here's the enthalpy value. Now the second equation, what we're going to do is write that in reverse. When we write that in reverse, we need to swap the sign on the enthalpy. So that's all that's done. All right, so then we're going to take the first equation and the second equation in reverse, and we're going to be able to cancel out some things. And let's see how these cancel out. So on the left side, we have these three components, which I'm highlighting. On the right side, we have these three components, which I'm highlighting. What we can do is cancel out what's on the reactant side and product side if they're the same. For example, ozone and ozone, there's just one of each. So we can cancel those out. Now we have molecular oxygen on the left and right, but they're in different coefficients. So all we do here is just find the difference. This would be 3/2 minus 1. You can just do that in your calculator, or you can write this so that it, with the common denominator of 2, so it'd be 2 over 2, which is still 1. So 3 minus 2 over 2 is 1/2. And then just organize it without writing what's canceled, and then rewrite what's left. We get nitrogen monoxide plus 1/2 O2 produces NO2. So we're on our way. The other thing that we can do is to get the enthalpy value. We just do the difference, negative 198.9 plus 142.3. We get 56.6. Now this doesn't give us exactly the equation because our goal is to get nitrogen monoxide and singlet oxygen. And this is O2, so we still have a little bit more to do. What we can then do is replace our 1/2 molecular oxygen on the left with singlet oxygen. We can do that by using that third equation. The third equation is here. What we'll do is divide our third equation by 2 and then reverse its direction. So when we divide by 2 and reverse the direction, we're going to generate oxygen produces 1/2 O2, and then the sign changes and then is divided by 3. So it'd be, for flipping it, it'd be negative 495. And then we also divide, and we should get, and if I said divide by 3, it's because of the third. Let's divide by 2. So sorry if I said that, I can't remember, but we divide the third equation by 2, reverse its direction. So we swap the sign and then divide that by 2, we get 247.5. We can incorporate that equation in, and what we'll be able to do is cancel out our oxygens, and our oxygens will go away, and we can have that right here. So you could even write this part right here, NO plus 1/2 O2 gives NO2 in this value, right on top of this equation. That would allow the 1/2 oxygens to cancel, rather than rewriting these two again. You get nitrogen monoxide plus singlet oxygen gives NO2, and then you find the change in values just by taking the difference of negative 56.6 and 247.5. So a negative and another negative is going to be more negative. So negative 304 kilojoules per mole. So once you practice a few of those, I think it'll be pretty easy. They're kind of fun. Your goal is just to rearrange them and multiply or divide to get everything to match what your desired equation is. Right, let's move into the next example. We have example 10.8. It says, using data from Appendix 2, calculate the enthalpy of reaction for silver cation and chloride to form silver chloride. Strategy here is we're just going to look up these values from a table. If you had this on a test or on the final exam, they'd provide a table for you or give these in parentheses. So what we'll have here is, it looks intimidating, but it's really not. It just has these summation. Just to break this down, what we're going to do is add up together the enthalpy of the formation of the products, and then subtract the sum of the enthalpy of formation of the reactants. So we can look up these values, and there should be 3 of them: the silver chloride solid, chloride, and silver. When we look them up, they're all in kilojoules per mole. This is 105.9 for the solid, negative 167, or for the silver cation, negative 167.2 for the chloride, and negative 127 for the silver chloride. And what we'll do here is the product is silver chloride, so we'll write that first. That's the negative 127. And it's products minus reactants, so we'll do product minus the sum of the 2 reactants. The 2 reactants are 105.9 and negative 167.2. So then, just following the order of operations, we can do 105.9 minus 167.2. We get negative 61.3, and just rewrote that. This minus sign remained. So here's our negative 127 minus a minus is actually adding. So negative 127 plus 61.3. You get negative 65.7 kilojoules per mole. And then big thing here is, like, we know minus a minus is a plus, so watch out for misplaced or missing minus signs. If we lose track, then we could go the wrong direction. So it's fairly simple just to do the products minus the reactants, but just pay attention to the signs, if it's negative or positive. And if you put it all in your calculator will do exactly what you put in. So if you just keep track on there, you can do it. Or you can just think about it in your mind as you're writing it out. We'll go ahead and do example 10.9. Given the following information, calculate the standard enthalpy of formation of acetylene, which has the chemical formula C2H2. This is a gas used in oxyacetylene welding, and then some other uses as well, from its individual elements. And it gives us these 3 reactions. Carbon graphite plus molecular oxygen gives carbon dioxide, hydrogen gas, and a half of molecular oxide gives molecular oxygen gives water liquid, and then 2 parts of acetylene and 5 parts of oxygen. So this would just be the combustion of it or burning of it. It gives 4 parts carbon dioxide gas and 2 parts water liquid. We get the enthalpy of reaction of each of these. These are standard enthalpy of reactions. Strategy is arrange the equations that are provided so that they will sum to the desired equation, very similar to what we did before. This may require reversing or multiplying one or more, and for any such change, the corresponding change must also be made to the standard enthalpy of reaction. The desired equation corresponding to the standard enthalpy of formation of acetylene is these two. And you'd probably be given this formula of the carbon graphite plus the hydrogen gas gives acetylene. So then same thing as before, we're going to rearrange these, reverse them, get things to cancel so that we can ultimately get this equation. And then do the same thing to the numbers, and then that'll give us our value. So take a moment, since you saw the last one, to pause it. And if you need to, go back and rework that other one again, and then try this one on your own, see if you can do it. Alright, so now that you've taken some time to look at that, let's try to see if you got the right answer. So what we'll do for this is we're going to multiply the first equation and its standard enthalpy of reaction by 2. And then we get the following. And then don't forget to do that to the standard enthalpy as well. We'll include equation 2 in its standard enthalpy value. And then what we'll do is reverse equation 3 and divide it by 2. And then this gives, this reaction, and then this standard enthalpy of formation. Putting these all on top of each other, we can get some things to cancel out. Here's our 2 parts of molecular oxygen on the left. Here's another part of molecular oxygen, so that would be 2.5, which cancels with this 2.5, the same thing as 5/2 parts of molecular oxygen. We have 2 parts of carbon dioxide here and here, which cancels, and we have water vapor on both sides that cancels. So then we write what's left over. We get our 2 parts carbon graphite and the hydrogen, which gives acetylene. Not forgetting to have the numbers changed. Doing the negative plus the negative and the 1299.4. So we have these two together and this one. So we're going to end up in the positive direction, plus 226.6 kilojoules per mole. Remember that a standard enthalpy of reaction is only a enthalpy of formation when there is just one product. Just 1 mole is produced, and all the reactants and elements are in their standard states. And you'll learn more about standard state information if you take General Chemistry 2. You'll do some information with that. But for now, just being able to rearrange and play with the numbers, you'll be in great shape. Slightly different theory, but still just adding and subtracting. We'll take a look at example 10.10. And again, you don't need to memorize these numbers. These are all provided in a table, and you can look them up. So let's read this together. Use bond enthalpies from table 10.4 to estimate the enthalpy of reaction for the combustion of methane. And it gives us the formula already balanced. Has CH4 gas plus 2O2, produces carbon dioxide gas and 2 parts of water. Draw Lewis structures to determine what bonds are to be broken and what bonds are to be formed. And you can have the enthalpy changes for either bond broken or bond formed, and it'll be positive or negative based on if it's formed or broken. So drawing these Lewis structures, we'll have methane. Here's our 2 molecular oxygens. Here's carbon dioxide and 2 waters. So then just start looking at what bonds are broken and what bonds are made and write it out. And this is a lot of fun. These are kind of like puzzles, if you can make this fun. The bonds that are broken here, if you look at carbon in the product and carbon in the reactant, carbon in the product just has oxygens attached to it, no hydrogens. So that means we're breaking 4 carbon-hydrogen bonds. We can also see that the reactants have these oxygen-oxygen double bonds, but then in the product we don't have those. So we're going to be breaking 2 oxygen-oxygen double bonds. What is forming, if you look at this side, we saw what's breaking. This is forming a carbon-oxygen double bond, 2 of those. And then we're also forming hydrogen to oxygen, and there's 1, 2, 3, 4. We can look up the bond enthalpies from table 10.4. So a carbon-hydrogen, and before I give these values, if I haven't mentioned it yet, but especially with this, think of this as a cost. Like, how much does it cost to do it? So think about it as money, and we can wrap our minds around that with the energy and money concept. So this is like the cost of all of this. All right, anyways, carbon-hydrogen costs 414 kilojoules per mole. The oxygen-oxygen double bond has this cost. And then carbon-oxygen and CO2 is this. And then hydrogen-oxygen is 460. So then we need to figure out how many we have of each and then do the math. So looking at the 414, which is the carbon-hydrogen, we have 4 of those. So we multiply 4 by 414. And the 498 is for our 2 oxygen-oxygen double bonds. So we multiply 2. Then we will subtract the 799, and we have 2 of those. 2 carbon-oxygen double bonds. And we have 4 hydrogen-oxygen single bonds. Now, notice this is reactants minus products. So it's backwards so that you can see this is what it costs to break and this is what it costs to make. And then you can find out, is it a net gain or a net loss? Like if we're doing the accounting of like business accounting with math I'm sorry, with money, not math. You use math. I think you know what I'm saying, hopefully. So we do the math here and then do the difference and we get negative 785 kilojoules per mole. If it's a negative value, it's going to be favored. And you can get into spontaneity. Is it a spontaneous or non-spontaneous reaction? You start to look at that in another concept that carries over into second semester. So negative is going to be favored. We want to have negative. If it's plus, then it's not a net gain. Okay. So one thing to think about, use the equation products minus reactants and then the data from Appendix 2 to calculate this enthalpy of reaction again. We can compare our results using the 2 approaches. The difference in this case is going to be due to 2 things. Number 1, most tabulated bond enthalpies are averages. And by convention, we show the product of combustion is liquid water, but average bond enthalpies are usually in the gas phase. So there'll be some differences there. I don't know if I would do that. I think that might be confusing. So, but if you're really getting this stuff and you're curious, then do it. But I wouldn't do it just for practice or anything. So, all right, last one. Example 1011, using data from figure 4.8 and 4.10 in Appendix 2, calculate the lattice energy of cesium chloride. This is for all ionic bonds, which is a metal and a nonmetal. They're all usually types of salts, and it requires a great deal of energy to be able to break those apart and change phases. And if we tried to melt something like table salt, like sodium chloride, we're going to have to heat that up thousands of degrees. So these are pretty hefty values. All right, so our strategy here is using the Born-Haber cycle figure as a guide, combine some pertinent thermodynamic data, and Hess's law to calculate the lattice energy. So from figure 4.8, we can get ionization energy of cesium, which is 376 kilojoules per mole. From figure 4.10, we can get the electron affinity for chlorine, which is 349 kilojoules per mole. Then from Appendix 2, we can get our standard enthalpy of formation of cesium gas, which is 76.5 kilojoules per mole. The standard enthalpy of formation of the chlorine gas, which is 121.7 kilojoules per mole. And the standard enthalpy of formation of cesium chloride solid, which is negative 422.8 kilojoules per mole. So we have all of those values in a table. Write them all out, organize them as you wish. And then because we are interested in magnitudes only, we can use the absolute values of the thermodynamic data. And then also because only the standard heat of formation of cesium chloride is a negative number, it is only 1 for which the sign changes. All right, so let's plug all this in and then make some sense of it. So we have the products of, they're the final products of the, the enthalpy of standard enthalpy formation of these two values, 376, and the chlorine gas, where is it? 121.7. We have the ionization energy of these, and then we have the cesium chloride. So we have 376, 422.8. We can then subtract the electron affinity of the chlorine from it, and then we get 648 kilojoules per mole. This is a positive value. This is not favored. This would be a process for, basically, it's not going to combust. You don't want to burn this for fuel. Is another thing, like we do the acetylene fuel, which came out negative, is some kind of applications of that to think about. So some other things that you can get and piece together. Ionization energy is to put this as a positive ion, and then this is going to be to give this the electron. And then the standard enthalpy of formations are fairly standard that you can see. And then we have 1, 2, 3, 4 of these. And then our electron affinity value is going to be a negative. And then these first 4 are positive. So just kind of pulling that all together. Hopefully it makes sense. A lot of these are very similar, where you're just adding and subtracting and putting it all together to see what the total energy is, given a scenario of rearranging it. We can compare this to sodium chloride, which is 787, and we can see we have 648 and 787. I mean, different values, but they're both positive and both in the hundreds, and they're relatively close. Both compounds do contain the same anion. Both have cations with a +1 charge, and then the difference in their overall standard enthalpy is going to be due to the size of the cations. So the relative size of the cations determine the relative strength of their lattice energy. So therefore, because cesium cation is larger than sodium cation, the lattice energy of cesium chloride is smaller than the lattice energy of sodium chloride. It can't be held together as tightly because of its large size. So that wraps up Chapter 10. Lots of energy information. If you like it, then you'll be well suited and ready for General Chemistry 2 because we go deeper in it. If not, then just really practice this stuff. It gets much more in depth in General Chemistry 2 with this information. Alright, I believe that's it. We just did this in 2 parts. And continue practicing, and just one more chapter left for General Chemistry 1. Thank you.